Good morning. Yesterday we did at least something. We understood how the convolution type operator look like and formulated homogenization problem. I gave the definition of the family which admits homogenization. And then we introduced the probabilistic framework. I mean, we introduced the family of the probability space and the family of maps which form a dynamical system. And then all this topic and the notions were essentially improved in the lecture of Alexander. So yeah, so there was in fact more detailed presentation in explanation in the second course of lecture. So now I'm going to introduce, having this probabilistic framework, I'm going to introduce the random coefficients, because you remember, let me write one more time, the structure of the operator L epsilon. Epsilon is, well, down, is equal to 1 over epsilon to power d plus 2 integral over rd a of x minus y over epsilon mu of xy u of y minus u of x d, y. X over epsilon, thank you, y over epsilon, yes.
And u on the left.
And u here of x, yes, thanks. So that's how our operator acts on a function from L2, 2 of Rd, or in the case of the Neumann problem, L2 of Q. Well, and now we want to understand what it means that the coefficients are random stationary. Let me remind you of the way to define them in the case of differential operator, local operator. There our job, in fact, is much easier, because in the local case, we have only one argument here. So then we say that we take some function defined, some random variable defined on omega, which possess the required ellipticity properties, and then we say that the realization of this random variable along the dynamical system Tx is exactly our ergodic family of coefficients, which gives us the desired random coefficients, which are stationary. In fact, it's one of the definitions of the stationarity, as we discussed yesterday. But in our case, we have two arguments here. So the first impression would be to write just mu of omega 1, omega 2, to say that then we take, we assume that, of course, it should be symmetric with respect to this argument. Both of them, omega 1, omega 2, are from our space omega. That's a measurable function which possess all the required ellipticity properties. Then we take x and y from Rd, and then we write, okay, this of course should be some different name, because it's not the realization, it's the original random variable. And then we write that it's our desired mu of xy, mu omega of xy is just mu of to x omega to y omega. Of course, we want the dependence on omega only, and we write this way, but tilde, yes. But here we immediately encounter a serious problem. This is not a Carateo-Dori function. It's abstract space, and since we originally have just measurable function of two variables, and then we substitute them somehow on the diagonal, the result is not well defined. You remember that in order to have the trace on diagonal or on some function of x or y, in order to have them well defined, we need, typically we need the Caratadori condition. But here, in
Can you remind what is
Caratadori condition is a condition that the function is for one variable, not for almost all, but for all values of one variable, it is measurable and it's continuous with respect to another variable. So in one variable, it should be continuous, and another variable, it should be, I don't want to give very precise definition, but Caratadori condition means the function is continuous with respect to one variable and well measurable with respect to the other one. If we have these two conditions, then the trace on some continuous the curve, which is continuous function, let's say f of y or vice versa, is well defined. But here, what continuity can we speak about if omega is absolutely abstract space? So here we have two options to proceed. One option would be just to say that we have some function of particular form where the measurability is easy to check, and one of this class, and mostly in fact I will deal with this one, mostly in applications people deal with this one, is just mu tilde of omega 1, omega 2 is just the finite sum with any n mu j of omega 1 times mu j of omega 2. Or a little bit more general when we have different functions here, but then we have both jk and kj. Okay, there are many ways to make it symmetric. Symmetrization, yeah. But in any case, originally we should have finite sum of the products. Then there is no problem with measurability. It's well known that for the product function, we can define this easily. So if it's not symmetric, if it's different function, we just symmetrize them. That's the way to, one way to fix it. But then we don't need continuity. Measurability is, you remember that what we want of this function, we want it to be measurable as a function of x and y and bounded. But since after that, if we take the function sum mu tilde of t to x omega mu j of 2y omega, then this function, due to the property of the dynamical system, this function is measurable for almost all omega as function of x. This function is measurable for almost all omega as function of y, so the product is well defined as measurable function. And since we have a finite sum, the point is here that we cannot pass to the limit as n goes to infinity, even if the series converge. In the limit function, we face this problem with the trace on the diagonal. Well, then there are many examples. On the other hand, there are many particular examples which starts from the particular structure of the media and where it's not so easy to understand if such a structure exists or not. And in this case, it's easier just by hand to check that in each particular example to check. But there is another way, also commonly used in the mathematical literature. Look, we are mostly interested, so it was the first option. The second option is we are mostly interested in the finite dimensional distribution. Basically, finite dimensional distribution of our process is the only object we are interested in. The formal probability space, which is behind all our construction, is of no importance. You can imagine easily that mostly just mathematical tool to study the problem. So now the question is it possible to change probability space in such a way that new probability space is a metric compact, a metric space which is compact. Compactification usually is for free, but we want to introduce a new probability space which is equipped with some topology. And then we want this function mu to be continuous infected in both variables. It's symmetric. So if we succeed to do this, then no problem. If our function is continuous, then of course, and the group Tx should also be continuous in this case, and then no problem to define all this object. And it turns out that in a typical situation, it is possible. But it's very technical, so unfortunately I cannot explain you how to do this.
You could just from the very beginning say that let omega be metrical space.
Absolutely. Often people do exactly like this. But then if you take from physics some particular example, formally speaking, you should check that indeed there is a, let's say, you say we take a Poisson point process, we equip with balls around each point, we form function. Can we claim that in this case there exists a metric compact such probability space with metric compact such that all these conditions are satisfied? Fortunately, in this case, we can check directly that everything is measurable. We don't need this construction. But one example when it's easy to check, I can explain you. For instance, assume that the realizations we know from our model that the realizations are continuous and possess some nice properties. Then we take as our metric space is just the space of continuous function. Then locally, we introduce the measure induced by the original measure on the space of continuous function. New measure will be a Borel measure on this. Then we then take cylindrical sigma algebra, and in this way we obtain the compact, even Banach space of function with Borel sigma algebra and the natural measure generated by the original measure. So in this case, it's easy. If we know well the structure of this coefficient, L infinity space is not a nice space. It's not separate, so L infinity better not to deal with this. So as long as we say that it's just L infinity with certain bounds, it's not so easy. But if we have some additional information about our function mu, then usually it's quite straightforward to construct this metric compact. And in some papers you can see the statement that there is always possible to find a metric compact such that, well, so the second way is to make omega metric compact. In fact, this statement that it's also possible to assume that omega is metric compact is correct if we enlarge a little bit the set of this mu. But typically, if we cover all our realization, then it's not a problem. Well, and now let us consider, so far it was just abstract framework. I explained why we cannot do this in the standard way as we did for differential operator. Here we should be a bit more careful with the definition of random coefficients. But what about particular examples? In these particular examples, I'm not going to introduce the probability space or this particular structure. I will just explain how realization look like, and then you will have to believe me that, in fact, behind this there is always all these constructions. So first one, Bernoulli model. Well, first of all, there are, of course, we take periodic media and we consider random perturbation of periodic media. It's one of the classical examples, but I don't want to dwell on it because it's rather standard. I want to consider somehow more probabilistic examples when we do not perturb some regular structure, when we start directly with some non-regular structure. So Bernoulli model means the following. We take ZD, and then at each point of ZD, let's call it eta, we introduce a collection of random variables, psi eta. Well, eta may be not a good symbol. Let's write z small. XZ. The collection of IID random variable, which takes on two values. Even two or some finite number of values. Let's consider the case of two values. So xi z is IID, independent, identically distributed. Maybe I should write one set. Independent, identically distributed. IID. Random variables. And psi z is equal to let's say 0, 1, 0 with probability p, and 1 with probability 1 minus p, where p is some number strictly between 0 and 1, otherwise it's not interesting. So we consider this collection of random variables. To each vertex of the integer lattice, we assign some random variable, and then we do the following. If psi z is equal to 1, we draw a ball of radius 1/2 around this point. If psi is 0, we draw nothing. It's clear, yeah? So here we draw, here psi z is equal to 1, we draw a ball, psi z is equal to 1, we draw a ball, here psi z is equal to 0, we draw nothing. So it will be random, really random collection of balls, no periodicity, nothing like this. There might be large empty space, there might be pieces somewhere far away, there might be pieces where all the balls are presented.
Zero, right?
1, thank you, 1 here, yeah. Well, and then we do the following. We say that we take 3 constants, and if x and y are inside the balls, I mean inside the union of balls, each of them not necessarily in the same one, then we assign the value of mu mu1, which is a positive number. If X belongs to the union of both and Y doesn't belong, then we assign the value mu2. So if one of them is outside this collection of balls and another is inside the union, we assign the second value. And if X is not in the union of balls and Y is not in the union of balls, we assign the third value. This way we construct a function mu. And in this way, this function mu is getting, of course, shift invariant, but so far only with respect to the integer shift. So far, if we make the shift which is not integer, it is not stationary, it's only stationary with respect to ZD. But it's not a problem. We can consider additional random variable, which is uniformly distributed on the unit cube, and to add to this geometry this additional random variable. Then I will not even write it down, it's clear. And then for this geometry, perturbed additionally by this random variable, uniformly distributed on the unit cube and independent on all these variables, we obtain the structure which is now statistically homogeneous with respect to usual RD. Metrically transitive, yes. That's one of the constructions. So,
straightforward to connect it, right? Dynamical system and this measure preserving.
yes, it's a good now exercise to construct all these instruments from dynamical system theory and probability theory, but I'm not going to do this now. Just you should believe me that in this space, for this model, we can construct all these elements, and in fact, in this model, it's not difficult. The collection of possible balls, in fact, collection just of function which at integer points take value 0 and 1 will be probability space, then product measure will be the measure, first on finite sets. Then we consider cylindrical sigma algebra, use Kolmogorov's theorem to construct the measure in the whole space, and it will be exactly this. And then the group of translation is just, the dynamical system is just shift. So in this case,
You can call it Anderson model.
Anderson model if you want, yes.
Anderson Bernoulli.
Chronologically, everything was after Kolmogorov, right? Including Duke, yeah?
And dupe, yeah. Well, that's one model, and maybe, but still here, you can say that still here we start with ZD, which again, a regular structure. Now let me give you a structure which has nothing to do with ZD or any regular. Poisson, absolutely. How do you know? So the second model is Poisson point process. So first of all, what Poisson point process itself is, I will write immediately with intensity 1. Poisson process is a measure, is a map from omega to the set of finally locally finite point sets in RD. So for each omega, we have a collection of points which is locally finite. There might be some concentration, but still it should be locally finite. And it should satisfy, this point process should satisfy two properties. First, let me call this P of omega, that's the collection of our points, and the corresponding, since it's locally finite, I can, for each omega, I can enumerate them. I think, in fact, it's a nice exercise for young researchers here to show that we can enumerate them in a measurable way, and so I will call it xj of omega, the points of this process. It should satisfy two properties. First, the number of points in any bounded Borel set should be distributed, should have Poisson distribution with the parameter equal to the absolute value, the volume of Q, because intensity is 1. So is distributed, has a Poisson distribution with parameter and the second, for any collection of Borel sets of disjoint Borel sets Q1, Qn, the random variables so we have these two properties, and it turned out that up to isometric transformation, this Poisson distribution is uniquely defined. If we consider another one, that all the finite dimensional distribution will be the same. The finite dimensional distribution of this process are uniquely defined by these two properties. So we have our Poisson set. Then we construct the so-called Voronoi tessellation of this. That's tessellation. What it is? This construction is widely used in physics, in crystal physics, in many branches of physics. This is, and also in the theory of porous medium, it's one of the main models when they don't want to deal with a periodic structure. Typically, they use Voronoi tessellation of some point process, not necessarily Poisson. The distribution might be different, might be some dependence.
I know what is Voronoi tessellation, but I don't.
Yeah, I'm going to write it down.
I don't know how to translate tessellation in Russian.
Tessellation in Russian.
Разбиение Воронова. So, what by definition, we consider for each point xj, we consider all the points such that the distance from this point to xj is smaller than the distance to the union of all other points. And this gives us the corresponding cell around xj. I think just for pedagogical reason, I will write down the definition. So let's call it, okay, V, Voronoi Vj is equal to x from Rd, distance xj of omega. Of course, its construction is random. Everything depends on omega here. Typically, I will drop the argument omega, but is less or equal, it depends. It's always. Then the distance less than the distance from x to the p of omega minus x. The definition looks quite ugly but it's very easy to draw it. We take the middle line between these 2 points. We take the middle line between these 2 points. The middle line between these 2 points. Not line, okay, in the hyperplane, in fact, in d-dimensional case. Same thing here, same thing here. We obtain always, and it's an easy exercise for the students, we obtain always a convex polygon here. Polyhedral, yeah. And this polyhedral with probability 1 has only finite number of, it's a convex set, and with probability 1, all of them, we take for typical omega, so almost surely all the Voronoi cells are convex polyhedrals. So we have finite number of faces. Well, and then we introduce our, I go to this. Partition, but I think in Russian literature people say разбиение Воронова. Раздробление. I have never said раздробление Воронова in Russian, always разбиение.
Partition of unity, разбиение.
Yeah, but
Most in translation, not quite the same.
well, and how to define our function mu? You remember we wanted to give it's the last example, and I wanted to give example which has nothing to do with ZD. So far we have nothing to do with ZD, and then we define the following. For any point here, let's say x is here, we take any function of the geometry of this guy. For instance, distance to the boundary, or distance to this point, whatever. Let's say just for the sake of definiteness, let's think about the distance to the border of this Voronoi cell. So we take L of x is equal to distance from x to the dvj if x belongs to vj. And then we take the function mu of x, y, which is equal, let's say, 1 plus L of x, L of y, divided by, okay, if you want 3 plus L of x, L of y. This is a nice function. Of course, this one is non-negative. So this function is between 1/3 and 1. So all our conditions are satisfied. This is a nice function. And it's statistically homogeneous because it constructs in terms of the geometry whose distribution, it only depends on the geometry of this guy. Since the geometry is translation invariant, the law of the geometry is translation invariant, this function is also, its law is translation invariant. So it's a nice example how we can construct our random function, which is not related to any periodic or regular structure. It's okay. It's always when you want to construct something which has nothing to do with the regular grids, use Poisson distribution. That's the recipe. Well, so now we have these examples of random media. So we go back to our homogenization framework. And let me, before the break, let me just write down the definition of energy. You remember that I promised that we will use the variational approach, a variational approach in terms of variational convergence, namely gamma convergence. And I just write down the energy associated with our equation. This energy, I will call it E epsilon, is equal to integral over Rd, integral over Rd, A of x minus y over epsilon. Let me emphasize that this function is not random. Rd, thank you. Mu of x over epsilon, y over epsilon. This one, for example. U of y minus u of x square dx dy. And 1 over epsilon to power d plus 2, thanks a lot. That's our energy we're going to deal with, and we already mentioned that the Euler Lagrange equation for this system, for this energy, well, formally I should add here plus m integral over Rd u square dx minus 2 integral over Rd u f dx. And then the statement is correct. Then the Euler Lagrange equation for this energy is, for minimization problem, is an equation whose solution we study. And in variational approach, there are some advantages and there are some demerits, as usually. The advantage is, instead of power 2, we can consider any, in fact, power which is greater than 1. We can instead replace 2 with some power q, also here. And we can study nonlinear problem, and everything works. I can write down the so-called non-local P Laplacian or non-local equation with variable coefficient if I put here the coefficient q, which should be, of course, greater than 1. I don't want to deal with the case q is equal to 1. It's difficult. It's a difficult case.
Model, nonlinear model, just mathematical, or it has some?
No, in porous media they have many examples of non-local operator which are also nonlinear. In modern porous media, everything is nonlinear. So, well, so in this case, what is important that 2 is not a restriction. In fact, all the methods which, all the results which I'm going to present can be easily generalized to the nonlinear case. That's the advantage, at least one of them. There are demerits, namely, in many applications we face non-symmetric operators. If we use variational methods, no hope to use them. Euler-Lagrange equation is always, gives us always a symmetric, self-adjoint or symmetric, at least symmetric operator. So that's essential. That's an essential demerit. If we want to study a non-symmetric problem, then forget about variational method.